Okay, yeah. Okay, greeting. I'm Ning. I'm a PhD student at University of Canterbury, and I work with Vara, Karen, and Yunxin for the TAIAO program. So this project is about graph-based deep learning for sea surface temperature anomaly forecasting. It's the second study of my PhD project. So why forecasting sea surface temperature anomalies? So forecasting sea surface temperature and sea surface temperature anomalies could help forecast climate oscillations like ENSO and the near dipole, and also climate extreme events like marine heat waves. These climate oscillation indices and the extreme events are developed from SSTs. So if we could forecast SST or SSTAs, ENSO, ILD, and marine heat wave can be forecasted. So especially for marine heat waves and extreme climate events, it could lead to, for example, loss of species, loss of foundation habitats, and damage to aquaculture business and fishery. So here are some marine heat wave, historical marine heat wave in the last 10 years. So it killed millions of seabirds and parrotfish, as well damaged lobster fishery. So if we could with accurate SST and STA forecast, actions could be taken in advance to mitigate the impact of SSTAs, which could result in both ecological and socio-economic significance. So this work aims to investigate graph-based deep learning for 1 month to 2 years ahead of global SST and SSTA forecasts. Existing SST and SSTA forecast model could be divided into 2 categories. One is the physics-based numerical models, and another one is the statistics-based deep learning models. So there are a lot of deep learning models that they use convolutional neural network, LSTM, Unite, and transformer. But this kind of model, they use Euclidean data like sequences and grades as input and output. But recently some models like use graph neural networks as they use graph as input and output. So graphs are kind of data structures that like a network, which include nodes or vertices and edges and links. So, and graph neural network have been widely applied to some areas like computer vision, NLP, social network analysis, traffic prediction, molecular representation learning, and drug discovery. And specific for environmental domain, Jing have forecast something like weather variables, frost, stream flows, groundwater level, PM 2.5, and AQIs. So while resampling environmental grids as graphs, here are some reasons we summarize. So grids are special form of graphs. So grids are essentially lattice graphs, and graphs are more general and flexible data structure. And graph can better model climate teleconnections. And the graph can avoid the issue of missing value for land pixels in grid data, especially like some ocean variables, the values and continents are usually missing. And using graph can avoid the issue of computational receptive fields for pixels near the edge of grids. So these pixels have less influence on the computation of the feature maps by CNNs. For example, New Zealand is usually near the edge of some global environmental grid. And using graphs can also avoid the issue of rotation equivalence for spherical subjects. So the data set we use for this study is ERA5. So ERA5 is real analysis product. It's a global real analysis from 1940 to the present time, and we extract SST sea surface temperature from the data set. And here's the example of the SST map in February this year. And we follow TAIAO and Feng, this paper, and we use the climate data operators. It's a Linux command, and to pre-process the data into to a smaller grid, and divided data into training and test site. And for graph construction, I will skip this part because of time. So these are the constructed graphs. These are 4 example nodes. So you can see these nodes in Tasman Sea is well connected with many nodes in southern subtropical and temperate zone, and this node in next to Western Australia is just connect with the nodes nearby, and same for this node, it just connect with the node nearby. So these nodes were just this place is just affected by a single type of currents like West Australia current and the Benguela current. And for this node in Northeast Pacific, Northwest Pacific, and it's well connected with nodes in northern hemisphere and some nodes in southern hemisphere. And we also computing SSTA from the constructed SST graph. So SSTAs are values at nodes that are the departures from the average SST by month or the 30 years period at each node. And we also perform normalization on the SST and SSTA graph. Okay, for graph representation learning, we use GNN. So we selected multiple GNN classes to perform learning on the graphs. And in our first paper, we investigated these GNNs and figure out that graph state models outperform the other models with in terms of RMSE, possibly because the graph state provides scalable solution to produce banding for nodes in large graphs, and all graphs are large. And the inductive learning made it suitable for graphs that evolve over time. And for some other method, we also use the sliding window method to perform to learn the temporal pattern. So we input, for example, we use the window size of 12. So we input graph of 12 months before the target month and output the target month. So it's first thing, it's an encoding and then decoding process. We also use early stopping. It's patience of 100. So early stopping is a method to prevent overfitting. So we save the model dynamically and continue training for example, 100 epochs. If there is no better model, we use the saved model. And if there's some better model, we just update the saved model. So we also use recursive model to perform long lead forecast. So it's a widely used numerical weather forecast. So we use a prediction input the prediction back to the model as input. Okay. This is an overall results for one month ahead SST global SST forecast. So you can see our model graph state model outperforms the persistent model largely. So we visualize these results, and this is delta RMSE. So the red dot is a positive delta RMSE, means our graph state model outperforms the persistent model, and the blue dots are the negative RMSE, means the persistent model outperforms the graph state model. So you could see that at most places around the world, our graph state model has better performance. And we also use this paper studying marine heatwave in 2021, and they summarize the key marine heatwave in this century, and they summarize these 12 key historic marine heatwaves, and we select the nodes in these 12 regions, and to perform further analysis. So these are time series plots. So the blue curves are prediction and the orange curves are observations. And this scatter plot is more clear. So you could see at some places like Alaska and Bering Sea, like Northwest Atlantic. And and in the China Sea, there are some the prediction are accurate. But for this place, for example, like Baja California, sir, like Mediterranean Sea, you could see the prediction for larger SST are not very accurate. So this is some problem as well as North Australia. And we also perform a longer lead SST forecast up to 2 years. So this is time series plots. So we use 2021, 2022 for examples at these 12 locations. So we input SST of 2020 and predict for 2021, 2022. So you could see at some locations where their seasonality is more clear, the prediction is good, but for some places it's not very easy to make long lead forecasts like this with some vibrations. And yeah. And then we make SSTA forecast. So we have two ways to make the such prediction. One is directly using GraphSage. We train analytics GraphSage for SSTA forecast. Another one is to compute the SST prediction by the GraphSage. So could you see our models outperform the persistent model by small margin? So these results. And we still use these 12 locations. For example, so besides Alaska and Bering Sea and Northeast Pacific and one node at Northwest Atlantic, for the other 9 nodes, our models outperform the persistent model. And yes, here are the results compared. We may do some further analysis using the major ocean gyres and the currents. So we just put these gyres and currents on this map. So you could see there are multiple currents in this area. So like Alaska current, California current, and North Pacific current. So of the fact this area, so the SSTA here, their variance changed over time, so it's hard to predict. And for these southern temperate zones, it's affected by the cold currents from Antarctica. So it may be hard to predict. And also the subtropic southern ocean of subtropic area. So these SSTAs are possibly affected by Eichmann transport. So it's hard to predict. And we may use these are also the time series as the 12 selected locations. And you could see the SSTAs are more challenging to predict than SSTs, especially for these observations, these larger SSTs which are associated with marine heavies, they are usually underestimated. So they were tackled in my first study on my PhD project. So we formulate this SSTA forecasting task as an embedded regression task, and investigate some loss functions and the data ensemble method to tackle these predictions. And for SSTA forecast, we cannot just using recursive model to make long lead forecast, because the model is just predict a general trend and which not very accurate. So we need some other method to tackle the long-term temporal pattern learning. Okay, so contribution. So we propose simple and effective way to resample ERA5 SST grades at graphs, and we identify the graph city model among widely used gene class to be effective for global monthly SST and SSTA forecast. We achieved 1 month ahead SST and SSTA forecast with GNNs across the world that outperforms the persistent model, and we compare 2 ways of forecasting global SSTAs. And they both have advantages and disadvantages. So some other products, we produced 2 research papers. The second one, we finished the first draft, and it's being reviewed by my supervisors and revised. And we produced a software package that converts the ERA5 grids into graphs, and it's available on PyPy. And one data set is SST graphs data set, and we will upload the SST graph data set with our second paper, and some code repository and the Jupyter notebooks, so could be shared. Okay. So thank you all for your attention and your valuable time throughout the presentation. Yeah, any question?
Thank you, Ning. Any question for Ning? Take your time. I know it's a lot to get. I mean, like all these graphs, all these plots mean something to you. Will probably bring you into a new question. Do you want an afternoon tea? Oh, you got a question. Oh, yeah.
Are you accessing it daily? Are you taking it as a average for a week or a month? How are you accessing it? Because if you have access to daily for a long period,
Okay, yeah. Oh, so the ERA file provides a monthly mean data. So we use it's a monthly data. Yeah, monthly one. Yeah, monthly average. Yeah.
And you give a time period like 2 days or like 2 months or 6 months or for a full year, what you accessing?
Yeah, we
It's whenever we go across more than 6 months accessing. Just wondering how.
oh, so we make predictions from 1 month ahead to up to 2 years ahead.
Just 1 month.
Oh, 1 month. Yeah, every month.